So now our group going to present a report about Torricelli Theorem. So our group consists of 3 members, which is me, Arif Imran Ikhwan Surazi, Ravin Rash Anak Lelaki Siva Kumar, and Muhammad Fazli Fitri bin Sawal. So I'm going to talk about the abstract. In this experiment, we compared the measured and theoretical value of the velocity by using the Torricelli's law. We set the cylindrical cylinder to 3 different heights and measure the velocity. The result obtained is compared to the theoretical velocity by using the Torricelli theorem.
Assalamualaikum warahmatullahi wabarakatuh. Good evening. So move on to the next slide, which is objective. The first one is to calibrate a Bourdon tube pressure gauge using dead weight. Number 2, to prove Torricelli relationship by comparing the actual and theoretical value of velocity. So the next one is introduction of this experiment. The theorem of Torricelli is a fluid mechanics theorem referring to the fluid velocity flowing from the orifice to the height of the fluid above the opening. In daily life, Torricelli rule has practical application. The physical law establishes a significant relationship between the velocity of liquid released and its height in the container. The law clarifies the relationship in that container between fluid leaving a hole and the height of the fluid. A simple experiment to test the law of Torricelli can also be done by puncturing the bottom with a small hole using a soda bottle. The exit velocity decreases as the height of the reservoir decreases. So move on to the next slide, which is theory. Torricelli theorem will describe the velocity of a non-viscous fluid flowing from a cylindrical tank if we have a fluid standing at a depth of h in an open tank whose side walls are vertical, as shown in figure 1, with a hole created in one of the walls. So the equation is V equal to set 2gh. Equation 1, where V equal to velocity, h equal to the depth below the surface of the liquid, g equal to gravity of the fluid. The velocity of the fluid flowing from the spout is the same as the velocity of the single fluid droplet falling from the height of the container surface of the fluid. In horizontal direction, the water stream from the hole can be represented by the kinematic equation. In this case, at any point, the velocity v can be represented by the time taken t by the stream water to cover the horizontal displacement of the stream water dx by stream of water x. So the equation is x equal to vi times t. For constant acceleration, equation becomes si minus x naught equal to dx equal to vi times the difference between t plus 1 over 2, which is equation 3, where a equal to 9.8 meter per second square. So the last one, at an initial point of v equal to 0, equation 3 becomes dx equal to 1 over 2 a times the difference of t square, so it becomes equation 4. Note that volume v and volume flow rate of the cylinder can be calculated from the following equation. V equal to AHCW, equation 5, mu equal to A set 2GHW, where A equal to area of cylinder in meter square, H equal to height of a cylinder in meter, W equal to width in meter. So that's all from me. I will pass to my friend. Thank you.
Good evening. Now let's see the methodology. The apparatus was set up based on different height of stages. The measurement of height is between the floor and desired orifice. The cylinder was placed on H1, which is height 1. The cylinder was filled with water. The whole of the cylinder was closed using a finger. Once the desired volume was reached, water was stopped pouring. Finger was taken off from the hole. At the same time, the maximum distance of water projectile was measured using the clay and the time was recorded. Experiment was repeated by using different volume of water at different height of stages, which is height 2 and height 3. Height 1 is considered as the lowest, height 2 is higher than height 1 and height 3 is the highest. Reading was recorded in table 1. These are the results. This is H1, which is considered as the lowest. This is H2, which is higher than H1, and this is the highest H3. Now let's see discussion. Our first discussion will be explain your selection on dependent, independent, and constant variable. Our dependent variable is height of fluid and diameter of nozzle. Independent variable is distance of water jet from nozzle. Constant variable is density of liquid because we're using the same liquid, which is water. To verify Torricelli's relationship, the choice of these variables is to fulfill the objective of comparing the measured and theoretical value of velocity. This will be ultimately be split into two parts due to the hole diameter on the water velocity, which is the impact of water height on the water velocity. Our second will be clarify on how you can relate the Bernoulli equation with the Torricelli's law for this case. Show all your derivation and explain each steps. Torricelli's law may be derived from Bernoulli principle and relates the velocity of water leaving the orifice in the fluid filled container to the height of the fluid above the orifice. Torricelli's law is derived from Bernoulli equation by equating the potential energy in the static head of the liquid to the kinetic energy of the water leaving through the orifice as follows. This is the common Bernoulli equation. The P1, V1, Z1 is be taken from the datum, and P2, V2, H, and Z2 is taken from the height above or below. It can be anything. If above, it's positive. If below, it's negative. The P1, P2 is 0 since it is atmospheric pressure. V1 is considered 0 because P1 is considered when there's no pressure, definitely there won't be any velocity. So V1 is 0 since the movement of fluid is so small and almost 0. Z2 is 0 because we take the point as datum. So if we calculate everything, we put inside the 0 and we get Z1 is equal to V square of the datum over 2G. And if we rearrange the formula, we already find the Torricelli's law, which is V2 equal to square root of 2GZ1. Our third discussion will be percentage of relative error for theoretical and measured experimental values. This is the formula to find the velocity of the theoretical value, which is square root of 2gh, and measured will be x square root g over 2y. Y will be the height, which is the h1, h2, h3. Z, x will be the water projectile. As you can see here in the table below, I only use the values that we have to calculate the theoretical value and measured value. To find the percentage of relative error, we have to use this formula V theoretical minus V measured over V theoretical times by 100, which is the percentage. If I about to show the each step for each percentage of relative error in the form, the calculation will be too long. That's why I didn't show any calculations. So I just showed what are the percentage of relative error. If you see the average error for H1 is 28.67 percentage. For H2, which is 0.5645 meter, is the average error is 26.66. And one thing we have to consider is that everything should be in the same unit, which is meter. I choose meter. We can also use centimeter, but it will be more difficult because due to the point form. and now my H3, which is 0.7615, the percentage error, the average percentage error is 45.92. Our fourth discussion will be source of error and method to minimize the error. Our first error will be starting and stopping the stopwatch can be different for different, which can potentially cause inaccurate time taking. Releasing of finger from the hole can be potentially cause inaccurate time taking. This is because if you don't take out the finger at the correct moment, the experiment result will be different. Method to minimize the error will be obtain more accurate result by calculating average value. This can be obtained by repeating experiment several times. Our second error will be parallax error due to the observer's eye being positioned at the angle to the measured marking when taking measurement to calculate H1, H2, H3 and measurement for the maximum distance the water projectile. Because since the water projectile is too fast, you can't be too accurate on finding this kind of stuff, finding the measurement, and you can't tell that it's too fast and the observer's eye is on the correct spot. It's very difficult to judge that. So method to minimize this error is observer's eye should be parallel to the scale. You can like ask two people or more people to look at the measurement to be more accurate. Our third will be leakage occur when covering the hole in the cylinder tank. Hole is not covered properly. If we don't cover the hole properly with our finger, our V1 won't be 0 because the water started to flow already. So to minimize this error, we can use a tape or stopper to be more secure. That's all for me. Thank you.
Now I'm going to talk about a conclusion. In this experiment, we can conclude that the velocity of water jet depends on the height of the water. The velocity of water jet is directly proportional to the height of the water. For the horizontal nozzle cases, the velocity of the fluid at the center line will be slightly greater than that at the top and slightly less than that at the bottom, due to the differences in elevation. In general, we can safely use the centerline velocity as a reasonable average velocity. To ensure proper result obtained, measurement tool must have a reliable system setup that does not introduce source of error to the device. Make sure all the leakage in the setup of the measuring tool are covered before conducting the experiment. Several readings should be taken in order to obtain a more accurate result. Besides, ensure that the position of the eye is perpendicular to the scale of the measuring tools in order to avoid parallax error.